With over 8 years of experience in additive manufacturing, he has held notable positions including a research fellowship at Cranfield University's Welding and Additive Manufacturing Center and a postdoc role at Multiscale Additive Manufacturing Lab, University of Waterloo, Canada. He has authored more than 80 publications in fields and is the author of the first comprehensive textbook on additive manufacturing in India, published by McGraw-Hill Higher Education for UG and PG scholars. His research focuses on metal additive manufacturing, processing of advanced materials, and post-processing techniques, aiming to bridge the gap between sustainability goals and cutting-edge manufacturing. Today, he will share his insights on additive manufacturing for net zero application and post-processing, a topic that is both timely and transformative. So we are excited to have you with us. The screen is all yours.
Thank you so much. I'm just sharing my screen. Is it visible?
Yes,
Is
sir,
my
it's
screen visible?
visible.
Yeah.
Yes.
Thank you so much for the invitation. And so, myself, Jinoop, I'm a lecturer in mechanical engineering at Teesside University. And my topic for today is additive manufacturing, transforming manufacturing on the path to net zero. So on top of that, I'm leading a lab on laboratory for advanced materials and manufacturing process where we do a lot of developing new materials for applications, process optimization, surface engineering related research. And nowadays, most of our research are more focused on the net zero application in one way or other. So the contents, first I'll start with the university. I'll just have a brief intro about the university. Then I know you might have heard a lot about additive manufacturing in the last 2 days, but I just want to give my own point of view on additive manufacturing. Then how additive manufacturing and net zero can work together. Then some of the research case studies which I have done at different institutes during from my PhD onwards. I've selected some of the case studies for presentation. I'll quickly go through them and some conclusions and what lies ahead for the future. So before this, as it was mentioned earlier, so this was the ACT approved textbook that we launched in 2021, and the second edition is in progress. So we are planning to launch it sometime next year. So this book is available through McGraw-Hill and through Amazon or Flipkart in India. So please have a read and let us know your feedback. And some of the materials that I am presenting in on specifically on an introduction to additive manufacturing is taken from this textbook. So coming to the university, Teesside University is one of the leading young universities in the UK, and it is top 6 in the UK for mechanical engineering, which I am coming from. So we are located in the northeast of England, as you can see in the map, with nearby cities Newcastle or Leeds. So this is our campus. So it's one of the very old campus. It was not a university previously. Then we got converted to university in 1992. And this is our beautiful town, the small town in the northeast of England, Middlesbrough. So those who are following football might be knowing Middlesbrough, so Middlesbrough Football Club. It's a great place to be there. Like it's small town, uh, be close to beach, and we have a good sightseeing as well near to the university. So as we have 5 schools in the university, and I belong to the School of Computing, Engineering, and Digital Technologies, and where we have 3 specific departments: one of Department of Computing, Department of Engineering, and Department of Digital Technologies. And one of the flagship projects of Department of Engineering of SADT is the Net Zero Industry Innovation Center, where we work very closely with industries on net zero innovation. So we are currently running multiple projects in this center where we focus on hydrogen innovation, decarbonization, circular economy, or a whole range of stuff which helps the industries to get into net zero. So we are currently running a project with Durham University on 11 million project on hydrogen innovation, on which I'm part of on one of the projects. We are doing with this a 30 million investment by Teesside University and the local authority and the government. So And our lab at Teesside University, we have a range of metal or a polymer 3D printers. So we have a polymer FDMs, we have metal AM which works on VAM, we have a laser for surface treatments, we have multi-material systems which is clay and ceramic. Then we have a range of polymer printers ranging from material extrusion, wet photopolymerization, material jetting, etc. And then we have a Siemens connected curriculum where we work with Siemens to develop softwares. So we have softwares which can do for design for additive manufacturing, tool path planning, which are all part of the Siemens connected curriculum. So first of all, I would like to start with what is additive manufacturing, which you might have heard previously itself. So additive manufacturing is a process of joining materials to make parts from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing and formative manufacturing methodologies. So if you break this definition, this is the ISO or ASTM definition. If you break this definition, it is a process of joining of materials. It starts from a 3D model data. It involves layer by layer buildup of material. Then it's not a subtractive technology or it's not a formative technology. So these are the five criteria of qualification for a process to be known as additive manufacturing. And when you consider that, these are the different names that are in the market. So it started with 3D printing. People called it rapid prototyping for some time. People call it layer manufacturing or solid free format fabrication. And there are different names for this technology, but now it's standardized as additive manufacturing or AM. And the basic difference is you take a paper and then print on a paper. That's a 2D printing, while you have a filament and you convert, or a filament or any shapeless material, and then you convert it into a 3D component. It's called additive manufacturing or 3D printing. The one of the things that we written in our book is how additive manufacturing is similar to the natural processes. It is similar to natural plant growth. It is similar to how a brick masonry is. You just add material layer by layer and build a structure. So, and so it's a natural process. We didn't have the technology to use it for manufacturing, but now we are using it for industrial manufacturing. Why is it very important? Mainly because of the complexity that it can bring in. So when the technology was conceived in 1986, uh, the major aim was to make complex shaped components which were not possible with subtractive manufacturing or other manufacturing techniques. Because as the complexity increases, the cost increases in conventional manufacturing, while in additive manufacturing, the cost almost remains constant. For example, if you consider such a complex shape, it is very difficult to manufacture these sort of structures by using common manufacturing methodologies. While if you use additive manufacturing, you can employ the layer by layer technique and then make complex shapes. Again, it leads to reduction in the lead time. It can remove a lot of steps in the industrial manufacturing, like tool procurement is not required. Raw material procurement is avoided because it can start from the beginning instead of waiting for the final design. No need of extensive planning, documentation, and drawing. So it removes a lot of steps in industrial manufacturing. And again, it gives you material design freedom. You can join multiple materials. It gives you mass customization. So it helps to combine the two extremes of manufacturing. One is custom manufacturing, another one is mass manufacturing. So you can combine them and then form a component which can be made in a number of number of units can be made at the same time. All of them can be of different designs as well. Integrated components. So we are currently working on a project in which we are trying to make smart components by integrating sensors to 3D printed parts. Then it's sustainable, which is the topic that I'm going to cover more today. So we'll come to the details of it later. Then logistics freedom. So we designed the part in one part of the globe and sell it across, and then we can print it elsewhere. So that's the freedom that the technique gives. And how is it connected to net zero? So we all are trying to achieve net zero. So the UK goal is to achieve net zero by 2050. Almost all the countries want to achieve net zero. What do you mean by net zero? And this is something that we're going to discuss in the next slide. But if you see this, the progress has been very slow, and we are still relying on the conventional fossil sources, and we need to move towards working towards a net zero. And Net zero is a balance. It means balancing the greenhouse gases we emit with the amount we remove from the atmosphere. So we can't avoid emissions. So it's not a realistic situation where we say that we'll avoid all the emissions to the environment. It's not possible. But it's one way. If you're releasing certain amount of CO2 gases, then we need to find a way to take them back. So this is how the industry is going towards. This is the aim of the different sectors now. So if you see the carbon footprint, industries contribute to 20% of the carbon footprint. And if you check the CO2 emissions, the share of manufacturing sectors is around 22% in 2019. The data is from 2019, it might have increased now. So this is a very important case to be considered, and specifically the climate change is really concerning, and we need to work towards reducing the impact of our industries or the manufacturing sector on the climate. So in this, like, what is the road to net zero? To achieve net zero, there are different ways that we need to work on. One is reduce our reliance on switch print media and switch to online communication, decarbonization, diversify our investments from fossil fuels towards carbon neutral investments, engage with our supply chains to reduce emissions, optimize our business travels to our events, change our behavior to improve energy efficiency, and reduce our reliance on fossil fuels in core business activities. So there are different ways in which we can work towards net zero. And one of the ways advanced manufacturing or additive manufacturing contribute is by decarbonization. I would like to take one of the case studies from a company in the UK. It's called 3T Additive Manufacturing. They have published a road to net zero by 2032. The aim is to achieve net zero emissions by 2032 by different ways. Like, they compared how additive manufacturing, they made a technical document and they try to compare how additive manufacturing is important to achieve this decarbonization or net zero. So according to them, the metal AM slashes weight by 45,000 kg if this is traditional, while additive manufacturing is only 1000 kg. If it comes to reduce material extraction, so again, this boils down to the extraction of materials, and the extraction of materials can also be reduced significantly, and the carbon footprint of a part can also be reduced from 106 kg to 4 kg. This is one specific case study of a part, but we can see the impact that additive manufacturing or advanced manufacturing techniques can bring to the decarbonization. Then they propose three different strategies to achieve net zero. One is complete value chain, then factory automation, digital integration. These are different ways in which they want to do it. But their mission is to have a net zero digital certificate for each and every product that they are manufacturing. So what happens is, when you're trying to make a part, so this is what their CEO says, it's very long, but if I want to take certain extracts from that, there are the supply chain strategy is really important. The scope 3 emission means the emission that is generated during the transit or during logistic. So there will be a situation now that the companies will need to have a net zero digital certification. And if they're not following those certifications, or they're not working towards achieving net zero, then they need to pay the carbon taxes. Then the price goes up. Then the customer needs to pay more to buy their product. Then the customer will go to another producer or another manufacturer. So at the end, the company start losing their market. So this is how the industry is moving forward. Like, we need to have net zero goals in each and every stage, not only from the manufacturing point of view, but in the supply chain point of view. We should have certain certifications which can help people to work towards net zero agenda. So industrial emission reduction is one of the major goals. So in UK, we have the Net Zero Innovation Center. So the one of the aims that they have considered is the reducing the emission from high carbon emitting industries, mainly the oil and gas. So we are progressing in emission reduction through that enables remotely operate assets, reduction of CO2 emissions, reduction of emissions. So There are different ways in people are working towards reducing the industrial emissions, and one of the techniques that is being used is additive manufacturing, and one of the techniques in this particular project is wire arc additive manufacturing, where they're trying to use VAM to make oil and gas components so that they can reduce the carbon emission. So this is the way the things are moving forward. And if you start seeing the sustainability point of view, you can't always say additive manufacturing is very sustainable, because if you see this, if you start breaking down the process into different steps, in the raw material production, obviously additive manufacturing requires powders or filaments to be made, but they should be an ingot in the beginning. So ingot manufacturing is there. Then we go for an additional step of powder manufacturing. So if you see here, there is an additional step of material manufacturing here, which adds to the total amount of energy that is consumed. While if you go to the printing process, again, it's energy intensive. If you see, it is 50 to 100 kilowatt hour per kg, while die casting machining is less than that. In terms of polymer as well, the same. The ingot production of the major synthesis is around 50 kilowatt hour per kg. Then you convert it into resin or powder or a filament. Again, it consumes 10 kilowatt hour per kg. Then it goes to a printing process where it consumes around 10 to 20 kilowatt hour per kg. So again, you can start splitting the stages, and then you can understand how AM also contributes towards this sort of energy consumption. So we can't, from this image, it's clear that we can't always say that additive manufacturing is very sustainable, but we need to find ways to prove that, or we need to find ways to establish how additive manufacturing can be fruitful for achieving net zero. So if you see this particular life cycle analysis, so in a conventional part, the raw material production happens, and the product manufacturing happens, the product use happens, and then the last is end of life or landfill or recycling. If you come to additive manufacturing, we have two stages here. Not only the raw material production, as I mentioned earlier, we need to have raw materials. At the same time, we prepare the powder or the wire that is required for manufacturing. Then we go for product manufacturing, product use, and end of life cycle. So in the raw material production stage, additive manufacturing tend to have a higher energy consumption. Then again, AM material manufacturing, product manufacturing, again, additive manufacturing is going to be energy intensive. So if you consider these three stages, then you can't justify the fact that additive manufacturing is sustainable, because if you see here, energy consumption is more with additive manufacturing. But if you come here, the product use, where the product is actually used for the engineering application, in that stage, the energy consumption is very high for a conventional part as compared to a AM part. What is the reason for that? This is mainly because of the optimization or the energy or the weight shape or the design topology optimization that can come into picture. So if you start comparing the parts in terms of the product usage, then additive manufacturing has got a longer benefit, because you can print parts which are lightweight, which enhances the life, it can reduce the fuel consumption. So a lot of other advantages, right? So this leads to the uh, what you can say, the energy reduction, the energy consumption in the life stage of the product. So this is where the actual environmental impact of additive manufacturing comes into picture, rather than be focusing on the material part. Oh yeah, material part also plays an important role, because we can recycle the materials, we can use them again for manufacturing. But uh, again, if you consider the product usage stage, it is having a better impact on the sustainability as compared to the material production stage. These are some of the case studies where additive manufacturing has been used for sustainability. If you see the aerospace bracket case, which are printed using additive manufacturing, then if you use laser powder bed fusion in the product stage, 1 kg reduction in the weight results in a product part save of 90K to 120K liters of fuel per annum. So, and AM part reduced buy to fly ratio of about 10 is to 1 to 1 is to 1. So if you say the buy to fly ratio is reduced from 10 to 1. So there is significant cost savings, significant material savings with this. Then again, if you say about material recycling, we have a lot of savings, custom overproduction, fuel efficiency. If you consider gas turbine parts, we can optimize the design using additive manufacturing, and fuels can burn better if and 1% efficiency in efficiency can lead to a huge amount of cost savings. Again, for other applications, spare parts, autoclave applications. So there are different case studies that people have done, and it shows that additive manufacturing has got benefit in different stages. Like some can be in the product use stage, some can be in the product manufacturing stage, some can be combination of product manufacturing and end of life. So it varies, but additive manufacturing has got benefits at different stages, and it is dependent on the specific user case. So what is the roadmap towards sustainable manufacturing and additive manufacturing? First is to gain transparency of materials and process. So nowadays, like, we don't have much of information about the raw materials being made already manufacturing, and most of the AM material manufacturers doesn't provide us the CO2 emission, uh, CO2 emission during the manufacturing process or the raw material production process. For example, polyamide. 1 kg of polyamide results in 7 kg of CO2 emissions. So this is one of the uh, material manufacturers given that information for polyamide 12. But for other materials, for all these metallic powders that we are using or the wires that we are using, we don't have this sort of data that is available. So this data is really important. And then once you have this data available, then you can develop this life cycle analysis database. This life cycle analysis database will give us a lot of information on how energy is being used at different stages, and then we'll be able to understand how is for a specific product AM is a better process or not. Again, coming to the third one, predict environmental impact before printing. So as I mentioned, life cycle assessment is really important. So before you go for a part, before you go for printing a part using additive manufacturing, you need to understand whether, from an environmental point of view, additive manufacturing is better or conventional manufacturing is better. For that, you need to have a sophisticated software or a LCA analysis network where you can understand the environmental impact before printing itself, and so that you can make a decision whether you need to go for conventional manufacturing or additive manufacturing, considering the environmental point of view. And the real work starts mitigate AM harm to the environment is the final stage where we need to start optimizing the AM process, because AM was not a process which was developed for sustainability. AM was a process developed just to make complex shapes. But as we move forward, AM is getting into a sustainable manufacturing process. So how can we use it? By optimizing the powder usage, optimizing the inert gas usage. A lot of energy is being used. People talk about multi-laser additive manufacturing, you dumping a lot of laser energy to the material to melt it and make dense structures. But one thing we need to understand is how much energy is being used, and are we harming the environment by doing that? So we need to find a so in the past we used to optimize additive manufacturing process for material properties, densities, mechanical strength. But I think it's time for us to consider the CO2 emissions or the harm we are creating to the environment also as a factor when we optimize additive manufacturing process. So in this context, the last topic is additive manufacturing for hydrogen, where a lot of research is now happening. We are also running a number of projects in this area, trying to use additive manufacturing for hydrogen application. As you all know, hydrogen is a clean fuel and it's going to be used in the near future. We are also working on with a lot of industries on using hydrogen for different application, mixing with natural gas, using understanding how hydrogen behaves with the materials. So additive manufacturing is one of the techniques that can be used for the hydrogen application, especially for storage, transportation, and different sectors. Now I will go through some of the research case studies which I have worked on during the past few years on additive manufacturing. I'll be quickly going through them considering the time limitation that we have, but if you have any queries, feel free to drop me an email and we can discuss further. So the first project I am trying to discuss is a project where we used laser DED system for making a nickel superalloy based heat exchanger, which I was done in RRCAT. So the build volume is 250 by 250 by 250. We have a 2 kilowatt fiber laser and a CNC manipulation, dual powder feeder. The main aim was to develop a prototype heat exchanger made of Hastelloy X and nickel superalloy, basically for the energy applications as a secondary side heat exchanger. So the main challenge that we had was there is no data available on this material. So it is very crack sensitive and defect sensitive material, and we need to make this large size component. So we had to break it down into different stages. So we started with single lines. So we did the process optimization. So this is a roadmap on how you start with a project or a material, and then you build towards a final structure. So we started with single lines, optimized them. We developed the process parameters based on the continuity of the tracks and the quality of the deposition. Then we went into the deposition of the large structures or the build structures or wall structures and identified the process parameters that can be used for making these wall structures. We did 3D scanning on these parts to understand how the process parameters affects the geometry. And then from there, we optimized the process parameter for the wall structure. Then we went to the bulk structure where we deposited multi-track, multi-layer structures to make a block. And then we characterized them. We optimized the process parameter, which can give us high density. And high density is a major goal and with a flat surface. So then we went down to the microstructure analysis. As you can see, non-homogeneous microstructure is there. We can see a lot of cellular dendritic growth. And as opposed to conventional manufacturing, we can see a lot of preferred growth along the 100 plane. And if you compare the mechanical properties, so the most important question that people continuously ask is how additive manufacturing properties are as compared to conventional properties. So in this case, what we observed is a higher hardness and a higher mechanical strength as compared to a conventional material. Then we went to different post-processing. So one of the study we recently published is on sequential layer by layer remelting, where we used SLLR as a process to remelt the material during the manufacturing. And then we could reduce the porosities, we could improve the surface quality, and then at the same time, we could homogenize the material. So if you can see that uh, surface roughness reduced significantly, the density, the porosities was reduced significantly, all the lack of fusion porosities that was formed in the material got reduced significantly, and we could achieve high density. Also, we could refine the grains to some extent. I won't claim it as a very high refinement, but we could refine the grains to some extent, and which would have resulted in an improvement in the mechanical properties in the base structure. Again, we did find the grain structure analysis. The initial additive manufactured part is a fine grain structure in the as-built condition. But when we did solution heat treatment, which is one of the heat treatment that is prescribed for this material. And when we did that, we could get recrystallized grains at 1177 degrees Celsius, and we could get grain and homogenization of the grains. We could get rid of the preferred orientation as well. And the properties are brought very close to conventional. So we did mechanical property evaluation from room temperature to high temperature, and we could compare it with the conventional material, and we could see that the mechanical properties are brought very close to the conventional conventional Hastelloy X, which is used for the standard engineering applications. And then we went into the development of this heat exchanger. It has a long struggle. We had failed channels in the beginning, then we started developing the process. So when you start making these sort of channels using additive manufacturing, the major part is the fine optimization or fine thin line between the different process parameters. We need to optimize these process parameters carefully to obtain these channels with a high quality. So we could find this narrow gap where we could optimize the process, and then we develop the code, and then we start developing this heat exchanger, which was around 200 by 200 by 200 millimeter cube. So this is produced and subjected to testing. But again, this was a long project which took more than a month to make this heat exchanger. Then I worked a lot on functionally graded materials. This was published around 5 years back. where we tried to develop this with for IIT Kanpur and IPR and for IGCAR as well, where we did copper and nickel FGMs, we did ferrero and stainless steel FGMs. So functionally graded materials, for those who are new to this, these are materials that are manufactured which has a gradual change in the composition from one end to other end. So as we move from one end to other end, we have slow change in the material composition. So we had, in this case, we had copper and nickel change. We had, in this case, we had a variation in from Delero, which is a nickel-based alloy, to stainless steel. So we mix the powder in advance, we pre-mix them, then we deposit them layer by layer by different compositions, and then we get this structures. Then the recently one of the works that we did was on copper and stainless steel FGMs, where we varied the composition of copper and stainless steel. Then we can see how the copper and stainless steel gradation has happened, and we can see how the copper particles are getting distributed in that matrix. And we could observe a lot of cracking in this particular case because they doesn't this two material doesn't go together. They don't work well together. So we can see phase separated morphology in copper and iron rich zones. Trapping behavior is seen. We can see the trapped copper films, and it increases with increase in the copper percentage. And we could develop these sort of wall structures from here. We could start from stainless steel and go to pure copper with a gradual change in the mechanical properties. You can see here how the in the copper stainless steel direct joint, we can see how the mechanical properties in the interface has changed drastically in the interface, while you can see the gradual change when we do the FGM. And we could see that the mechanical properties of 50% graded structures are at par with the copper and the direct copper CSS, while 20% grading has got more defects, mainly because of the more thermal cycling it has undertaken. We have more cracks in this particular case. Then another project that we recently did and published was on laser surface melting, which is a laser post-processing technique where we used a continuous laser, actually continuous fiber laser, to polish the surface of already manufactured parts, and we could see a lot of improvement in the surface roughness. So we developed a process window where we can go for the melting actually. So surface over melting, there are two different zones, surface over melting and shallow surface melting. So if we go for, we need to identify based on our requirements. So this is the beauty of this process, like we can control the laser intensity, and then we can move from, we can select the zone where we need to work on, and then we can get the desired outcome on the surface. So as per our requirement, we can control the laser energy per unit length and then get the desired surface quality. Another case study which I was doing when I was in Canada at Formation Engineering as a postdoctoral fellow at MSAM, Multi-Scalability Manufacturing Lab. So we used a 1 kilowatt fiber laser based DED system to make in different components for the industry, different industrial commercialization scenarios. So we did these sort of structures or dome structures. Again, these structures are more very important to be made of additive manufacturing, because if we go for conventional manufacturing, conventional machining, it ends up in wasting a lot of material. So additive manufacturing is going to be really important for such applications. So we developed the process methodology for that. Then we developed we characterized them completely. We could use it. We could find that these are highly dense in structure, and the geometrical variations are within point plus or minus 0.5 millimeter, which is acceptable for that particular application. And then we went on to make the spherical tanks as well. Then we also worked on developing overhang geometry. So this was a work that we published in Additive Manufacturing Journal. So we tried to make this sort of a overhang geometries by using a, if you see this sort of a bended pipe structure, we can see that in a specific layer, the thickness of the layer is less at one side and higher in the other side. So in a specific layer itself, we need to have a lower height at one zone and a higher height at other zone. So we need to play with the process parameters here. So you can see that in the one particular zone was printed with a higher scanning speed, while the other zone was printed with a lower scanning speed. So you can, within a layer, we can vary the height. So again, this is the beauty of the process. So we have each and every point can be controlled, just like the material design freedom, as I mentioned earlier. We can control the material at each and every point. Here you can control the geometry at each and every point. So you can change the velocity of the laser beam at different points, and there will be gradual change as we move from this area to the from this side to the other side, and then we can get the right geometry. So we did a lot of geometrical analysis, CT analysis, microstructural analysis. So there is a slight variation in the grain structure. If you go from a area which is lower speed, so area which is having a higher speed has got a finer grain structure, but the area with the lower speed has got a coarser grain structure. You can see the difference here, but the impact on the hardness is not very obvious, I will say. It's not very high. So you can see that how the variation has happened. It's the fine grain structure area has got a higher hardness. The lower grain structure area has got a lower, sorry, the larger grain structure area has got a lower hardness. But again, the variation is within the range that we are expecting. This is one of the challenging projects that we did is on laser cladding applications of thin wall tubes for nuclear applications. So it's a 0.5 millimeter thin tube, and we use additive manufacturing to create claddings on this. It's really challenging because the tube can damage instantaneously when the laser hits the surface. So if you can see the initial trials that we did, that the tube was getting punctured at each and every stage when we did the project without any additional steps. Then we went into extra shielding. So we used argon gas for an extra shielding. So we used a pipe and fit. We used argon gas as an extra shielding mechanism. Then what we could do is we could get rid of this damage within the interior of the tube, and we could get good bonding between the cladding and the tube interior was also protected. So when we go to the cross-section analysis, we could see this continuous variation in the cross-section. There is no defect formation except for some micro pores, which is generally expected in laser cladding or laser additive manufacturing. But we can see that there's a smooth gradation. You can see that the tube is here, the mixing zone is there, and we have the clad region. So there's a smooth change in the composition from the tube to the clad region. And this material that we have deposited here is a highly oxidation sensitive material, oxidation resistive material, and these materials are used a lot in the next generation nuclear reactors. Another project that we did was on quality control on LDED. So we were trying to use deep learning to predict the surface defects. So if you can see here, so this is a in additive manufacturing, you can see there will be variation in the surface quality. You can see here there are these sort of dips and highs and lows will be there on the surface. The surface quality depends again on the process parameters, the standoff distance, number of parameters governs that. So we developed a deep learning technique. So one of our PhD students was the next developed this deep learning technique for predicting surface defects. Then we used that to control the geometry of the part. So we predicted at which parameters we can generate these sort of defects, what will happen actually, and then we used it to control it. So what happened is we used two different strategies. One is scanning speed control, other one is laser and scanning speed control. And then we used them to get a flat surface. So this sort of structure was the initial phase, and then we brought it to the actual flat component. So we could see how the geometry has improved. But again, if you see within a layer, we are varying the scanning speed. Within a layer, we are varying the laser on and off as well. So does that impact the material properties? Obviously, there is a slight impact, but not very much. Very huge impact is not there. So if you see the defect formation, again, they are largely micron scale porosities. If you see the gain, the defect formation is around 40 micrometers is the size of the defects that is seen. And if you see the again the cross section of the samples, the images are mainly showing gas porosities and all. So there is not much of an impact on the specific variation that he has mentioned. Even grain structure, the laser control has got a slightly fine grain structure, but the others have got a similar grain structure. So the mechanical properties are also intact when we are doing this. So by doing this project, we could get the surface quality, but the mechanical properties didn't vary significantly as well. Some ongoing works that we are doing at the moment is on processing of Inconel 617 for nuclear application. One of my MN student has done this work. So we deposited Inconel 617 at three different energy densities. We made three different blocks. This is a powder that we use for that. So we could understand how. So the major finding that we could get out of this is the effect of energy density on the defect formation, the grain structure. We could see that S2 is having a higher energy density, S1 is having a lowest, and S3 is the middle one. So within that, we could see that the high energy density samples have got a lot of cracks in it. A lot of defect formation was seen on these samples. If you see the S2 sample, it has got a higher intensity of closed pores as compared to the other ones. So if you see S2 has got higher intensity than S3 and S1, and which again is showing a clear correlation between energy density and the defect formation that is generated in the samples. Grain structure, if you see the variation in the grain structure, the higher energy density samples has got a coarser grain structure, and as we move towards a lower energy density, we are getting a finer grain structure. And then we did ADS mapping, which again, because of the lower energy density that is being used in this project, we were getting a the lower scanning speed that we were using in this project, we were getting a finer composition, finer or a uniform chemical composition for this particular parts. Then we did EDS mapping. We could see that the EDS maps indicates a variation in the orientation of the grains. Again, we could identify how the cracks are being deposited. Again, if you see this, the cracks are very high for samples which are made at higher energy density, and we could see that I've not put much of the analysis in this particular slide, but the whole work, it shows that the energy density plays an important role in controlling the grain size of the samples. Again, the hardness and the XRD data indicates, XRD data shows that the phases are similar, but if you go to the hardness values, you can see again the lower energy density samples has got a higher hardness value, while other samples has got a lower hardness value. Then the next project that we are working on is on using additive manufacturing. This is one of ongoing work that we have, which is using additive manufacturing for hydrogen applications. Then, so we use the 3D printer to print nylon samples. Uh, and then the 3D printer, you printed the nylon samples, then we used the samples for a hydrogen exposure. So as I mentioned, we have the Net Zero Industry Innovation Center, where we try to expose different. We have a reactor there, as you can see in the image. This reactor can be used for exposing different materials to hydrogen environment. So you expose the materials to different hydrogen environment, then you can understand how the material behavior changes. And we could see that the normal nylon has got something sort of a this sort of swelling has happened for IT manufactured parts or 3D printed nylon. So the major aim of using this project was on developing a understanding the compatibility of polymeric materials for hydrogen transportation. Because in our what is happening in the UK is we're trying to change the conventional gas pipelines to a hydrogen pipeline. So we want to understand how the conventional polymeric materials are behaving in the hydrogen environment. And one of the application is using 3D printing, because this 3D printing can be used for these sort of components like the valves or the control transportation pipelines or the storage tanks can be made of 3D printing. So we wanted to understand how 3D printed nylon also behaves in hydrogen exposure. So it's a part of an ongoing project on exploring different polymers. So sideline project is on exploring how 3D printed nylon can also fit into this role. So then we exposed it and we could see that this sort of swelling behavior, but this swelling behavior is mainly, and again, we could see a lot of impact on the mechanical properties. So this is the configuration that we use. The 260 is the printing temperature, 50 is the printing speed, and 80 is the infill density, 80%. And this is the typical tensile strength and modulus and strain and break for the conventional nylon parts. And what when we sorry, yeah, conventional nylon parts, and after exposure to around 100 bar of hydrogen for 72 hours at 20 degrees Celsius, we could see that the tensile strength dropped by 49 megapascal, modulus dropped by 3 gigapascal, and the break strain increased by. So it means that the material is getting more softened as we are exposing it to hydrogen conditions. And if you see the DSE and TGA map, and you can understand that there's not huge difference in the material behavior, but you can see that the degradation of material has changed. The char that is developed at the end of the process has changed. The decomposition has happened at a slightly lower temperature, which means there is some weakening of the material. A lot of studies in progress. This is just early results, but we are still exploring this direction a lot on understanding how different materials get work on the hydrogen environment. So we also did a life cycle assessment of 3D printed nylon just to compare how whether we can use 3D printed nylon as an alternative to conventional nylon for this of a hydrogen application. And we could see that if you consider the environmental impact slightly higher for 3D printing because of slowness of the process and higher power consumption it has. But if you go to the economic performance, material efficiency wise, it is better. Then there is no significant variation in the water depletion, marine toxicity, etc. But again, the outcome that we could get out of this project is that selection of 3D printing for this sort of application, additive manufacturing for this sort of application depends on the volume, emission regulation, energy sourcing, and the cost priorities that we have. So, to conclude, as we move forward, the main challenges in additive manufacturing is shortage of qualified materials, speed and productivity, repeatability and quality assurance, industry-wide standards. We need end-to-end workflow and integration. We have software limitations, security issues because of the digital nature of the process, and skill set gap. That's why we are conducting these sort of events where we train people on additive manufacturing. Opportunities, a lot of opportunities are there in machine and software development. We still need cheaper softwares for additive manufacturing. The existing softwares are really costly. Process development and control, a lot of still we don't have a lot of process available for different materials. So if you see there are millions of materials available in the world, but we don't have process for each and every material for additive manufacturing. So process development is an important area to work on for researchers. Material or feedstock development, we need to have local feedstock developing companies. There are very few players in the market and people are over dependent on these companies, which increases the lead time again. So we need to have local manufacturers for the feedstock. Design for additive manufacturing. So unless you use the capabilities of additive manufacturing, that is design or lightweighting, reducing the uh, reducing the buy to fly ratio, we can't actually go for the benefits of this technology. The benefit of technology is more when we use use the actual advantages, that is getting the uh, cost or getting the designs which is optimized for the reducing the cost. Modeling and simulation is another area for understanding because, as you know, as you have seen in the slides as well, there are a lot of defects that is formed in the process. So a lot of modeling and simulation is required for further understanding this because the process is really costly. Running an additive manufacturing system is not very cheap. Characterizing and testing, yeah, qualification of materials, it goes hand in hand with process development, quality control and assurance, application development, then education and training. We need to have more courses, more people trained on this because as we move forward, the technology is evolving and we need to have a trained workforce because according to me, as we move forward, more and more industries will be adopting additive manufacturing because we need to start developing things and locally. We can't rely on the supply chain for a long period of time because of the uncertainties. Any war can change the uncertain, can make the things uncertain, and the supply chain will have a huge impact. So the major issue is that we need to be self-reliant. Every country should be self-reliant. So local manufacturing is important. So every country should, or every company should focus on using 3D printing or additive manufacturing at some point where to stress on the local manufacturing, and which again pushes towards more education and training requirements. So my present research directions are nickel superalloys for aerospace and again titanium for medical applications. Sorry for the mistake there. Characterization additive manufactured structures for defects, metallurgical analysis of additive manufactured structures, design optimization of additive manufactured parts, additive manufacturing for hydrogen application, post-processing of additive manufactured parts, and wire arc additive manufacturing of metallic alloys. So AM is an advanced manufacturing process used to build complex shapes, started with rapid prototyping, moving towards metal additive manufacturing. Careful material and process selection is necessary for successful AM implementation. Various case studies show the benefit of implementing AM in different sectors. AM requires systematic investigation and training for high quality parts. Research opportunities are still plenty to improve the process. Before I end, I just wanted to introduce some of the things that we are doing. So we are having a special issue on 3D printing for multifunctional application sustainability, which is now running in Sustainability Journal. So if you are interested in submitting any of your works to this special issue, feel free to contact us. Then there's another journal. I'm an editorial board member for this journal. This is Research in Material Science and Taylor and Francis. So if you are interested to submit any of your research to this particular journal, feel free to contact and please go ahead and please let us know if you are interested. So thank you so much. And if you have any questions, I'll be happy to answer.
Any query from the audience side may be written in the chat box. So we have a query.
Yep.
Good morning, sir. First of all, thank you for the great presentation. And sir, I have a question regarding the wire arc additive manufacturing process. And as you shown in the SS copper combination functional graded material, you have deposited with the help of LPBF. And when we do, what are the challenges that you face? And there are some challenges that I am also facing regarding the wire arc additive manufacturing for depositing the copper. And so can you give me some idea regarding that, how can to overcome the for depositing the copper